Hi everyone. Sorry that I couldn't make it to class today. Bear with me too. I'm losing my voice, but I will do my best to make an effective learning video for you. So, last time when we talked, we were talking about composition being a binary operation. So, it's an operation between two mappings that produces another mapping. We then ask the question, well, if it is indeed a binary operation, then does it have an identity element? Meaning, is there a map that acts as the identity map, such that that identity map I, if you compose it with another map alpha, no matter which direction you compose, you should just get the same map alpha back out. So we found this map. It turns out it was just this, it's simple. It's just, you can think of it like y equals x, f of x equals x. The identity map is you plug something in and the element that comes out is exactly what you plugged in. We showed that the identity mapping is one-to-one and onto. And so the next question that we want to answer is, now that we know we have an identity element, what about inverses? Do mappings have to have inverses? Do all mappings have to have inverses? And if it's not all, then which ones have them? So we know, for example, from matrix multiplication that not all matrices are invertible. The same is true for mappings. Not all mappings are invertible. And by the end of this lecture, we will have identified an equivalent condition to saying that a mapping has an inverse. And so let's start by just defining what it means to be an inverse. So if I have a mapping alpha from A to B, we say that the mapping beta from B to A is the inverse of alpha, provided we need two things. Well, if we think back to how an operation works, a binary operation, when you have an inverse, it should be such that when you operate with an element and its inverse, you get the identity out. So here we are operating with maps and we're using composition. So it should be such that beta composed with alpha gives me the identity, and also alpha composed with beta gives me the identity map. Now we need to think a little bit though about the identity map on which set. If you remember this notation that we used up here, we said that the identity map is I sub S. It accepts values from S and outputs values in S. So I would invite you to think for a moment, pause your video. If I look at beta composed with alpha, what type of element does it accept and what type of element would it be outputting? Can you use that to determine which set beta composed with alpha is the identity on, and which set alpha composed with beta is the identity on? One way to help yourself see which is which is you can go to the schematic drawing of our graphs, of our mapping. And let's say that this is the set A, here's our set B. We know that if you take an X value and you plug it into alpha, and then you get out some alpha of X, what we're saying is supposedly if I then take beta and go back the other direction, this X value that I started with is really beta composed with alpha of X. So here, what we see is that we started with an element in A, and under the composition, we essentially just ended up at the same spot. So what I've just drawn here is a loop, essentially. We started at X and we looped back. This loop is equivalent to following the map beta composed with alpha. Therefore, we can say that beta composed with alpha is the identity on A. If I were to start by plugging in a value in B first and taking beta across this way and then coming back using alpha, I would have the identity on the set B. The notation we use once we know that the inverse exists is we denote beta to be alpha inverse using this superscript of -1. To be clear, when I say alpha of inverse like this, that does not mean 1 over alpha. When a mapping does have an inverse, that's when we call that mapping invertible. So let's take a look at an example to understand how this works. So we're already familiar with a couple of functions and what their inverses are. So in particular, you can ask yourself, if I have the function f of x equals e to the x, then what's the inverse of f? It's the natural log function. It's typically when you're solving equations with the exponential function and you're trying to get the x out of the exponential, you apply the natural log to both sides. That's because you're using the fact that the natural log is the inverse of the exponential function. So we know that our inverse is going to be some function g. It's supposed to go in the opposite direction than f. So it should go from r plus to r. And we think it's g of x equals the natural log of x. So let's check. If we're going to check, then what I need to make sure is that g composed with f gives me the identity, and f composed with g gives me the identity. So let's take a look. If I say g composed with f of x, first of all, where is this x value coming from? Well, since I am plugging into f first, then I should be starting with an x value that comes from the domain of f, which is r. So when I go ahead and I do this, we know this is defined as g of f of x. That's like saying g of e to the x, but g just takes the natural log of whatever you plug into it. The natural log of e to the x is x, and this is true for all x in R. So therefore we can say that g composed with f is the identity map on R. I would pause your video and try to compute f composed with g. Check what you get, figure out which set it should be the identity on. Okay, so we do f composed with g. This time we are plugging in g first. F of g of x is going to give us f of the natural log of x. And if I do that, I'm going to get e to the natural log of x, which we know is just x. Since we began by plugging an x into g, we started with, we needed to make sure we were plugging in a positive real number so that the natural log was defined. And so this is true for all x in R plus, which means we can conclude that f composed with g is the identity on R plus. So therefore we can say g equals f inverse, because going back up or scrolling, remember all it takes to be the inverse is to be a mapping, which we accept that the natural log function is a mapping. It passes the vertical line test. It's defined for all values on R plus. And the composition in both directions, when you compose this function g with f, gives us the identity map. So that is the definition of g being the inverse of f. Now let's take a look at an example of a function that is not invertible. And keep in mind here, we need to pay close attention to how the mapping is being defined, what its domain is, and what its codomain is, because that certainly influences whether or not the function over that domain will indeed be invertible. So to get a feel for what's going on here, our function is sine x, which we're familiar with. Let's scroll down here, and I've drawn you a picture of the graph of sine x. So we know that it oscillates between 1 and -1. So let's suppose that an inverse did exist, and we said that g was the inverse of f. Keep in mind f of x is sine x. Then we know that if g really is the inverse, the composition of it with f, no matter which side we compose on, should give us the identity map. So in particular, what that tells us is that if I do g composed with f of some x value that I plug in, what should come out is x, and also f composed with g of some x is supposed to give me x back out. Let's start by just taking a look at this top direction of composition. So what this tells me is that if I plug an x value in. So looking at this top composition, this is telling us that essentially, let's say f of x is some y value. So I plug in an x value into sine, I get out the y value. Then if I talked about g composed with f of x, that's supposed to be g of f of x, which is g of whatever that y value is, but x is supposed to come out. Okay, so this tells me that when I plug an x into f of x and I get the value that comes out on the graph of sine, g is supposed to then accept that y value and take me right back to the x that put me there. However, if we take a look at our graph of the sine function, for example, I could look at what happens at the y value of 0. So here's the line y equals 0. So imagine I was trying to figure out what g of 0 should be. That's like saying take the y value equals 0 and output the value of x that this should be x such that sine of x gives me 0 out of the function. So it's all the x values or the x value that produces a y value of 0. But notice there are multiple values where that happens, 0, pi, 2 pi, etc. And so then that begs the question, should g of 0 be equal to, should it be equal to 0? Should it be pi? Should it be 2 pi? We don't know. What property would this violate? The fact that we can't decide which x value took us to the y value of 0. What property of a mapping would g not have in this case? This is saying g is not well defined, because we're basically saying, should g of 0 equal 0? Should g of 0 equal pi? Which one should it be? Now, the issue that caused this to happen, what property is f missing that caused g to be not well defined? Well, the graph didn't pass the horizontal line test, and since it didn't pass the horizontal line test, that corresponds to failing to be 1-to-1. And that's what happens when we investigate, one direction of the composition. So we haven't taken a look at F composed with G to see if anything goes wrong there, but right now we've seen that G composed with F, we're going to have problems. If I try to make a function be such that G composed with F is the identity map, then we're going to run into this issue of G isn't even a mapping to begin with because G isn't a well-defined function. So that actually gives us a one way to prove that the sine function is not invertible. So we're going to come up here and we're going to write up this proof. Now, the overall structure of how we were thinking through this is we basically said, well, suppose that we did have an inverse of F, and then we showed that something went wrong. And so the structure of the proof that this takes is going to be contradiction. So writing up one of the proofs, we're actually going to do a second proof. This is going to come from looking at what information we would get if we were to look at the composition in the other direction being equal to the identity. Let's write up this proof first and then we'll come back. So this proof is by contradiction, which means we're going to start out, we're going to assume that F is invertible. And then we're going to let G be the function from R to R such that G equals F inverse. So we want to show something goes wrong. Looking back at our argument, the key to showing that something was going to go wrong was taking a look at the what goes wrong with G composed with F supposedly being the identity, and then arriving at the fact that G is not well defined. So that's what we need to sort of exploit in our argument, and in fact we have a counterexample to being well defined just by looking at these values, looking at what happens when G is at G of 0. So coming back up here, we know since G is the inverse of F, then it should be such that for all x in the reals, when I look at G composed with F of x, that should give me x back out. So in particular, that should work when I plug 0 into my function, and it should also work when I plug pi into my function. So let's take a look at that. So this is saying that 0 should be equal to G composed with F of 0. Well, we can actually compute this. This is G of F of 0, and we know what the sine of 0 is. That's just 0. And so on the one hand, 0 is supposed to be the value of G of 0. And we also get that if I plug pi in, this is supposed to be G composed with F of pi, because again, it's the identity on the identity map. And that would be G of F of pi, which is just G of sine of pi. But that's G of 0 again. So what we have now is we've just said that G of 0 takes two different values. On the one hand, it's equal to 0, and on the other hand, it's equal to pi. This is a contradiction. What we have demonstrated here is we've come up with a counterexample. This shows that G is not well defined. But remember, in order to be an inverse, you have to be a mapping, which means you have to be defined and you have to be well defined. So this is a contradiction. G must be well defined to be the inverse of F. Thus, F can't be invertible. What we found is that if we tried to make a mapping that satisfied G composed with F equal to the identity, then we would find that that mapping actually wasn't a mapping. It's not well defined, and that's our contradiction. So here, the issue that we had that we were able to sort of exploit is that F is not one-to-one. So now let's go back down and say, well, what if we, had chosen to investigate this G composed with, or sorry, F composed with G in that direction instead? What if we had done that? Well, let's see what happens. Remember that G is supposed to accept values from R because that's the way F is written. F is written as mapping from R to R, and G accepts values from the codomain. So if I'm supposed to have that F composed with G of X is X, then it should be such that I do this for all X in R. Remember, what G accepts is a Y value, and it tells us the sort of the X value that we get out that took us there. And so from that perspective, you may prefer to consider this like in the form F of G of Y equals Y for all Y in R. That's saying the same thing, but it might feel more graphically like the same. So if I come up here though, that's telling me that I'm supposed to be able to plug in, say, Y equals 2 and get an X value that took me there. But this isn't even going to give me any value because the sine function never hits Y equals 2. So the issue we have is that what if Y equals 2? We know that the sine of X does not equal 2 ever. That's true for all X there. So what this is telling us is that on the one hand, F of G of 2 is supposed to give me 2 out. But on the other hand, that's like saying sine of G of 2 is supposed to give me 2. Because F is just accepting sine of G of 2. If you want an extra step here, you can say this is F of G of 2. Make a replacement for F. That's how we're getting this sine of G of 2. Well, that's not going to happen. Sine is never equal to 2. And so what we have is, how do we define? The question is, how do we define G of 2? No such value can be such that when I plug it into sine, I get 2 out. And so the issue we're getting here is that G is not defined. And it's not defined for any Y that's not between -1 and 1. In particular, it's not defined for 2 in this example that we just looked at. So coming back up here, we can ask ourselves, well, what went wrong with our function? When we were taking a look at this before, from the perspective of that first proof we did, we asked the question, what property is F missing that caused G to not be well defined? I can ask a similar question, what property is F missing that caused G to not be defined? So let's write that down. What property is F missing? The key was G had to have codomain of R because that is how, G had to have domain of R because the codomain of F was R. And that leads us to the situation where we're left wondering, well, what do we do with Y values that are not in the range of our function? When you have Y values in your codomain that are not in the range of sine, that's like saying our function is not on 2. So F is not onto. So we can go up and we can actually write a proof, an alternative proof. I mean, technically we've already proven that F is not invertible simply by showing proof 1. But if we had looked at it a different way, we could use the fact that F is not onto in order to come up with an alternative proof for why F is not invertible. So this is also a proof by contradiction, since we basically assumed F was invertible and started working with this function g. So assume F is invertible and let g from R to R such that g is F inverse. Then this is saying for all x in R, F composed with g of x is supposed to give me x out. So in particular, if I do F composed with g of 2, that's supposed to give me 2. But we said that is saying sine of g of 2 is supposed to give me 2 out. It's a contradiction. We know that -1 is less than or equal to the sine of g of 2, which is less than or equal to 1. So that tells us that there wasn't a g of 2 that could have done this. That's like saying, so no such g of 2 exists. In other words, G is missing this property of being defined. That keeps it from being a mapping. And since G of 2 can't be defined, so since G can't be defined on R, F is not invertible. So again, the issue that we have here is that F, our sine function, is not onto. And in fact, we can summarize this right here. Proof 1 uses the fact that F is not 1-to-1. Proof 2 uses the fact that F is not onto. The issue when you're not 1-to-1 is that G is not well defined. And the issue when you're not onto is that G is not defined. That means in either case, if you try to make a rule that satisfies the composition being the identity on either side, then what you find is that rule is not actually a mapping. So the last example, looking at why sine is not an invertible function, actually reveals to us the key properties that are necessary and also sufficient in order to say that the inverse of a map exists. So a mapping is invertible if and only if it is 1-to-1 and also onto. So if you're ever asked to prove that a mapping is invertible, you could instead prove that that mapping is 1-to-1 and onto. Or if you know a mapping is 1-to-1 and onto, then you can automatically say that it's invertible. And so since we have experience with these properties, then we're just making an extra extension to say when both of these properties hold, that's equivalent to saying our function or our mapping is invertible. Now the proof of this I am actually just going to post for you to look at and go through. It is a long proof. the individual components that go into writing the proof are all things that you should understand. I'm not going to ask you to prove this theorem on the exam, but I do think it's worth looking through as you're studying.